second week of this program. So for who arrived today, like you will discover in the next hours that like everything is in these three buildings. So here we are gonna have the coffee breaks and the talks. Coffee breaks are upstairs, and the next one is gonna be at 3:30. There are also some posters where coffee breaks are gonna happen, so feel free to check them. There are some desks in a nearby building that I can show you where it is later. And we are going to go for lunches in the ICTP canteen. And like typically we go all together after this talk, so that we can also show you where it is. Okay.
And the talk starts at 2:30 in the afternoon.
Right. The talk starts at 2:30 in the afternoon, more important than the coffee break. And yeah, so the first speaker of this week is going to be Fabian Bautista, and he's going to talk about gravitational waves with black-hole perturbations.
Great. Yeah. Yeah, thanks a lot. Thanks a lot to the organizers for the invitation to speak here. It's a great pleasure to be back in guest. I was actually a student at the ICTP back in 2015, 2016, so it's always nice to be back to you. So I realized that I can't prepare like a lot of material, so but feel free to interrupt me, ask questions if there's something that you don't understand. It's fine, we can cover everything. So let me start first of all by thanking my collaborators. Some of the work that we're going to be discussing here is based on the wonderful computation of many people here, including local organizer Christopher, and several works have been done with different groups of people, and we're going to discuss them here a little bit. So I've divided the talk in 3 or 4 stages. So I'll start with the motivation, for us to have in mind, like the big picture of what is it that we are trying to approach the problem, and then we'll start to go more into the details. In particular, we're going to be interested in understanding a little bit the response of compact objects to external perturbations. Modeling them in a kind of effective field theory framework. So I'm going to explain what does it mean. But then, effective field theories, they usually are like blind to what is happening microscopically, right? So you need to find a way to understand what is happening microscopically. That you can either do matching to experiments, extracting numbers from experiments, or matching some UV computations. Like in our case, it's going to be UV computations. Many of them you are used to do, which is black hole perturbation theory, perturbations of compact objects in general relativity. So this is mostly classical. There is no quantum here, so sorry for those who like to do quantum physics. And then once you have kind of know everything about this microscopic physics, then you can start using those effective Lagrangians to study other observables. In particular, you're going to study gravitational wave observables. So this is what we have in mind. So basically, the aim of big effort of big teams in different parts of the world is try to do precision computations that are useful for doing data analysis in gravitational wave observatories. So this is the image of the first detection of the gravitational wave at the LIGO observatory, and it was a big breakthrough because it's a very, very small perturbations of space-time. So they remarkably agree with very well with the prediction from Einstein theory, and it was awarded the Nobel Prize in 2017, right? So big experimental effort. But actually, I want to emphasize that the theoretical effort is very difficult. It's very challenging to predict what is the form of this waveform that we need to use to do data analysis. So you could say, well, you know the theory, right? It's just Einstein's equation. You can plug a source in the right-hand side of the Einstein's equation. They are black holes. Black holes are vacuum solution. You put them, you invert these equations, and what is the wave? That's something very difficult to do because of the nonlinearities of general relativity. So could say, well, you can do, solve this equation numerically, but that's viable maybe to compute one waveform, right? But the LIGO detector, they have a big parameter space. So doing simulations, every data point of this parameter space is basically impossible. So not only that, you have 17 parameters to vary for each waveform. You have masses, spins, orientations, and everything. And that's not possible.
Can I ask you a question? This matching is with QGR, or there is some constant you need to keep for this matching?
So usually what people do is, okay, you have Einstein's equation, but maybe you can allow for deviation from general relativity. The way in which they parameterize them, sometimes they parameterize in the early spiral stage, some deviation from post-Newtonian theory, maybe some nonlinearities, but it's not very, what we all have done is like, okay, you compute a waveform allowing for this deviation, and then you kind of match to whatever you see, and then you see that this deviation has not it. But it's not very illuminating, the thing that they do. Sometimes you can put deviations which are not even physical, right? To have something that is not local. So it's not very clear for me that the parameterizations of deviations of general relativity are not really consistent. But anyway, this is the way people do it. So, with the time, we start learning to do it better. So instead of trying to solve the Einstein's equation for the whole numerical relativity program, what people do is use the fact that you have separation of the scales, and then start modeling the problem into different stages. So the first stage is what people call the spiral, where these compact objects are separated very far away from each other, and they move at non-relativistic velocities. So it's what people call the post-Newtonian part of the waveform. Then when these objects start radiating energy and angular momentum, they start to get closer to each other until gravitational pull is very strong. So now you are in the non-linear regime of general relativity. You have to do numerical simulations, and finally you have this very excited compact object that is radiating quasi-Riemann reach black hole state. So, but then doing the separation in the different stages of the waveform and then putting this together is something that's very non-trivial. So far the best way that we have to reconstruct the full waveform is known as the effective one-body problem, but there's still like many open questions of how to put all of these different parts of the waveform together in a very consistent manner. So, yes?
If I look at the plot there, I see the velocity goes from 1/3 to 2/3 along the process.
Yes.
So it's not really like you're going from a non-relativistic to ultra-relativistic regime. It always stays more or less in the middle.
Yeah, well, the thing is that because of these circular orbits as well, then what you mean by because of the visual theory, velocity and G contribution, you can get mixed. But I would say like 0.5, 0.6 is already very relativistic. It's not extremely relativistic, but like the object this big, this size, they already move very fast. Okay. So recognizing the theoretical effort, give this group of 4 people in the building next door. Actually, I was trying to align the picture with the different stages, contribution to different stages, but it was impossible. You should have placed them in a different way. So, Thibault and Moore is, Thibault is not for many things, but his pioneer work in this was in the early spiral post-Newtonian theory. Then, so Tchaikovsky, many of you know, right? He was the way of doing what a modern perturbation theory, in particular, to analyze the ring down phase of the signal, and Franz Pretorius was pioneer of doing numerical relativity computations. Finally, Alessandro Bonanno and Thibault and Moore were the one pioneering this effective one-body reconstruction of the full waveform. This was recognized in the Gravitational last week. So a big team of people coming not from gravitational physics but actually from collider physics has started to do is using the techniques that you use to compute observables for colliders and try to see if you can apply those techniques in the problem of binary scattering. So why can you do that? Again, because you have separation scales. So in this problem, two compact objects going around each other, you can define many different dimensionless parameters. So for instance, first parameter in there, epsilon, is the ratio between the sizes of these compact objects and the separation of these compact objects in their spirals. So this is why it's known as the post-Minkowskian parameter. In particular, in the early spiral, this parameter is very small. So you can, kind of expand Einstein's equation in different powers of epsilon and then start solving order by order for epsilon. It's also a velocity expansion parameter, so if these guys are moving non-relativistically, you can further expand the equations. So that is what is known the post-Newtonian theory. But then if you have objects that are rotating, there's also like a spin multipolar parameter, this zeta that I'm defining there, is basically the radius of the ring singularity of this black hole, so for instance something from a black hole, divided by the separation of this object. You can also expand the Einstein's equation, which in the case you have spinning sources ordered and solved ordered by Z. But for black holes, these three parameters, they are not all independent. So they have to satisfy the curve bound. So it's something that you have to be careful with. I'll explain a little bit later. But in principle, if you have these three set of parameters, you can expand your Einstein's equation kind of linearized way, and then you start building the curved spacetime adding one graviton at a time. So the compact objects, they look like point particles, and actually they look like elementary point particles. So you can think of them really as spinning point-like objects, and then they start exchanging gravity. So that's why it's a natural kind of setup to use all of the tools that you use for collider physics and try to start doing predictions for gravitational wave scattering. So there could be other scenarios. I think Ricardo talked about this one last week, which is the expansion in which you have one very massive object and the other one is very small. Okay, so you can do like a small mass relation expansion and the gravitational self-force. Or it could be the case in which the gravitational wave being emitted towards infinity has a wavelength that is much bigger than the size of the binary system. So you can do some kind of multipolar expansion, not for the multipolar expansion for this composite system. So for instance, the leading multipoles are just controlled by the bonding mass and the bonding momentum, and then you start constructing generic multipolar deformations of this compact system. So most of the things that I'm going to be telling you today will have to do with the early spiral stage where you have weak fields, maybe small spin. So what is it that people have in mind? Since these are basically like point-like word lines, they are interacting with each other by the exchange of gravity. So what people have been concentrating in the last 10 years or so is to compute, what would be the Hamiltonian of this system, order by order in the vertical expansion, which is the post-Minkowskian expansion. So just corrections to the Newtonian potential order by order in G. Right? So until a couple of years or so, the state of the art in the computation in the post-Minkowskian expansion was like a 4 p.m., 3 loops computation, which was very non-trivial. There's a group of many people working on this. There's a group in California, a group in Berlin, a group in Humboldt, and many other people working, doing progress towards computing correction to the Newtonian potential. This year, there has been progress going to the next order in a PM expansion. That the computation is not finished yet, but it's almost finished. So, a characteristic for this correction to the Newtonian potential up to this order is that these compact objects, they really look like point particles. Like the action that you put to describe the motion of these objects is just a point paradox. So finite size effects, meaning effects that will realize where you have a black hole or a neutron star or any other compact object, they will show up at next order g to the 6. So, some estimates of what is the precision that you need to have for your theoretical predictions in order to do data analysis in future gravitational wave observatories is that you have to go at least a couple of orders more in the cosmic constant speed. That is great.
Is it known that these are convergent expansions?
No, these are not convergent expansions. These are actually asymptotic expansions. So there is also a problem that you have to start thinking of resumations.
Do you know that they're divergent expansions?
They're not. They are.
Or they
asymptotic.
look like it? Or what do you actually know about them?
Well, things that we know is that you can compute an observable, and you start to see what this observable look like as a function of g. And then we compared to the true result. The true result, what we call is the prediction from general relativity. And if you are in the regions where the cosmic Coscan expansion is good, you get a very good agreement with numerical relativity. But when you go to strong field regimes, you get big disagreement. To get agreement with those, you have to resolve. There is no other way. The series will never see the strong field regime of general relativity.
So you stick it in some pade and it works, or what do you do?
Well, this is the part in which I say reconstructed the big waveform is not very trivial. The EOB approximation, for instance, what it does is kind of resums the geodesic motion, so all of this, because basically this G expansion is also expanding the geodesic, so but you know what is the geodesic motion. So put the geodesic in, it gets a little bit better agreement, but resumation of the series is something that people haven't figured out yet. There's still work in progress, and it's a big deal. It's not clear how to resolve this series. And so that's why many of us are working on this. So, but anyways, what I wanted to tell you today is not about the series itself, it's about very interesting effects which are the finite size effects. You would say, if you wanna tell me anything about finite size effects in the binary black hole problem, then I have to do a phi loop computation. And this is something very difficult for us to do. But there are scenarios in which these finite size effects they show up at early stages in the perturbative expansion, which are toy models. Instead of having gravitational wave, you have scalar waves. You can learn a little bit about the response of compact objects to this kind of perturbation. So today we're going to try to focus on these toy models. We're going to tell something about the gravity eventually, because the aim is to tell what would be finite size effect when you have these binary systems. It's going to be important for gravitational wave observatories in the future, but we are not there quite yet. But we are on the way. So then I told you there is a different expansion parameter, right? So there's expansion in the spin multipolar parameter. So people have also produced results not only considering point particles, scalar point particles, but since point particles, you can also add some spin to them, and then doing computations, correction to Newtonian potential also in that direction. So we'll come back to this maybe by almost at the end of the talk of when these two, as I told you that these two expansions, they are not independent from each other. In particular, they mix exactly at the order in which you have finite size effects. It's a very interesting regime to prove these two things. So, doing computation for binary black hole physics is very difficult. There is a simplified setup in which you can understand how a compact object reacts to external perturbation, which is just having a black hole there, sending a wave. This wave can be a plane wave, has some spin wave, right? Can be a scalar wave, electromagnetic wave. And it will be scattered by the potential of the black hole. Maybe part of it is going to be absorbed on the horizon of the black hole. And then by understanding all of these effects in this simplified model, you can extract actually a lot of physics related to how this object is reacting to this perturbation. So once you have understood this in the single black hole problem, then you can reuse this information to study the binary black hole problem. But there are different ways of doing this, and the objective that you have in mind is that you're gonna fix these numbers, like what people call the so-called love numbers, to tell you how this compact object react to external perturbation. They depend on regularization schemes. So usually these are numbers that they have some regularization running, and in particular we want to fix them in the scheme that people use to do binary black hole computation, which is dimensional regularization. So more people have computed this number in different schemes. That's great. We have learned about those, but we cannot reuse them in the binary black hole problem. So in order to be able to reuse them, we have to redo the computation. That's it. So okay, let's enter into some details before we study black holes. Let's just review what the linear response theory is in simplified model electrodynamics. Right? You have extended material, then that material into some external electric or magnetic field, and then this external field is going to start using some multipolar deformation, in this case the electric dipoles. And then if you sum of all of these little induced dipoles, you know that at first approximations, this total polarization of the material is also proportional to the external field that you have applied. So that's what we call linear response theory. Again, the linear approximation, but it works really well for characterizing materials. So this number, the coefficient of proportionality, is what characterizes the response of the material to external perturbations, electric or the magnetic susceptibility, and basically this gives you some interaction around for P dot E or E squared in the response theory. Right. So these numbers are very important. They are characteristic of how every material reacts to these external perturbations. And the question is, how do you tell? What can you tell about these numbers? How can you fix them from first principle? It's very difficult. So first of all, this is kind of like an effective field theory way of putting. You have this unknown coefficient that characterize the response of the system, but you know nothing about those coefficients. Just that there are some effective coefficients, right? You have an effective field theory. You can compute an observable, for instance, the differential cross-section of how these waves are starting off the material. And either you have a microscopic model of how all of these different dipoles are interacting with the external field, and then so put them in the Maxwell's equation, and then compute the same observable from the Maxwell's equation, compare, and extract this number from first principle. It's something very difficult to do. So instead, what we have been doing is reading these numbers from experiments. Right? We do material characterization spectroscopy. We're just going to the lab and measuring these numbers in the lab. Different materials, you have different. That's something characteristic for every material. So one can generalize this idea of not only inducing dipolar deformation in your material, but maybe there is some impurities in your material. Maybe you start using higher multipolar deformations, right? So the way in which I'm writing the more generic multipolar deformations are in this special derivatives, the L, and I'm again assuming like kind of linear response of the system to the external perturbation, so we have this electric field. But you can also allow for maybe absorption of some of this energy into the material. That's why from 2 copies E plus and E minus of the electric field. This is what is known as the Schrödinger-Taldish formulation. Maybe the electric field that you are putting this external field is time dependent, so you can allow for time variations of the external field. Right? And the most generic interaction, tidal action that you can write is coming over all of these possible multipolar formations. The coefficient chi ln is just going to be characteristic of the response of the material for every multipolar deformation. You can even write it in more like variant way. It's just because it looks nice, but the idea is that this action is going to be very similar when we study black hole perturbation. So for black hole, it's exactly the same, right? So, but unlike electromagnetism, you know, if I want to determine how the coefficient of how a black hole responds to external perturbation, I want to do it from experiments. It's very difficult. The sensitivity of the experiments at the moment do not allow it. So instead, you have to take the other route, which is maybe predict what this number look from some UV principle. So there is like a road that is well defined now how to extract these numbers in a gauge invariant coordinate independent way. So you know, this is not like flat space-time anymore. You have general relativity, you have curved space-times, you have a coordinate transformation. You can, you know, compute things in one coordinate system, and maybe this gives you something different in another coordinate system. So you need to make sure that these numbers that you are defining, they are the same regardless of the coordinate system you are using to describe the physics. So the method has like 3 ingredients. First, we're going to write like an effective way of like an effective theory model. This is something that someone at infinity will see about the interaction between the black hole and the external perturbation. So also I'm going to concentrate on asymptotically flat spacetimes. That's because the spacetime I can define the observables are scattering amplitudes. So people who do not do asymptotically flat spacetimes, it's a little bit more difficult, but there are some analogs, as many of you know. So then, now that I have an effective theory characterizing what is the response of this object to external perturbation, I will match those to the UV solution, where the UV solutions are provided by the black hole perturbation theory. I think that many of us in this room know how to. If I match these two, then I'm going to extract what is the prediction from general relativity for these numbers. But the advantage is that the prediction that I will do, it's really like coordinate independent gauge invariant. So really a property of the black holes and artifact gauge transformation. So I'm going to concentrate in 4 and 5 dimensions because as many of you have heard, you know, there's the law that black holes in general relativity in 4 dimensions, they have 0 log numbers. There is several people working in this effective theory that have proven that is actually true. But then some people say, you know, black holes in higher dimensions, they do not have 0 log numbers. And, you know, maybe in this talk we will learn exactly what people mean when they say there is no 0 log numbers. So I'll show you exactly what I mean. So, okay, let's start with the first ingredient. You know, let us write an effective description of how a compact object reacts to external perturbation. So, the perturbation parameter which you can play with is the wavelength of the wave that you are sending towards the black hole and the size of the black hole. In particular, if the wavelength is very big, much bigger than the size of the same compact object black hole, interchangeably, mostly thinking about black holes. So if the wavelength is much bigger than the size of this object, then this object really looks like a point particle, right? So the action to describe this, just a point particle coordinate action, and then the interactions are mediated by the gravitational field. We have the Einstein-Yilber action, and from now on, I'm gonna think of scalar perturbations of the black hole because it's just easier to write equations in the slides when you think of scalar black holes. But you know, the method just holds generally to where you are thinking of gravitational perturbation. This, you know, maybe some object, the other mass has some scalar charge, and there is a wave, and this wave will come and affect the other object. This is more like one. So that's the point particle description. Nothing weird in there. But then eventually, you know, if you send wavelengths which are comparable to the size of the object, then you're going to start proving the finite size structure of this compact object. And parameterization of the finite size structure, I'm just going to write it exactly in the same way in which I wrote the multipolar deformation in electromagnetism, right? So I have L multipoles moment. I have the external field now at pi plus, pi minus, so to allow for absorption down the horizon of the black hole, and allow magnetic time dependent external fields. The coefficients of proportionality, you know, once you write these operators in a basis, meaning you take care of integration by part and everything. In the context is just basically writing this operator is the basis of SO3. Then these operators are linearly independent. So that's what I'm going to define like log numbers. Every coefficient for every linearly independent operator in the effective description. So if you do dimensional analysis, you count what is the length dimension, for instance, of these coefficients. It is, if you're in the generic dimension, d minus 3 plus 2L multipolar deformations plus n time derivative. And so the only scale that you have at hand is the size of the object itself. So these numbers should be proportional to the size of the object to this power. That's like the naive counting in effective theory. But you could have guessed, this naive counting is too naive. Because usually you have a UV divergences, you have to renormalize Feynman integrals, and then you start introducing the normalization group scales. So then these numbers will not become just a number, they will become also logarithms of these normalization groups. So this is nothing, it's just the analog of what happened in quantum electrodynamics, right? Massive delay can get normalized because of the divergences. So normalization is not something about quantum filtering, it's something about effective filtering. Particularly it shows up also in classical filtering. So
this comes
yes.
because you approximate it as a point-like object.
Exactly.
Yeah.
So it's just a size. We're kind of integrating out this UV, this freedom that tells you that this object is from the same color. That's why you just have some of these variances in effective computation.
Yeah, but by integrating out, but
By integrating out, I mean that I'm writing this effective action that doesn't know anything about what is the nature of these numbers. I'm just saying, if I knew how every single degree of freedom is being excited from the external field, then I could predict what these numbers are. I'm just like someone sitting at infinity, and what I see at infinity is point plus some multipolar deformation. No, nothing about what is happening. No idea what is happening at the scale of the final things or something like that.
you're not actually integrating out of a integral from.
No, it is. It's possible. Yeah. I'm just using the symmetries of the object to write an effective action. But you could also get this from a pattern integral. Okay, so the way in which these logarithms arise when you start computing log numbers in 4 dimensions, for instance, if you send a scalar wave and then it hits the black hole in 4 dimensions, they start arising at 3 loops. So the reason is that at 3 loops you start finding reader variances. And this arise in the dynamical set of the computation. Basically, when you allow for the external field to be time dependent. Instead, in 5 dimensions, you start to get a logarithm correction to these log numbers, even in the static set. So if you send a wave of spin 0 and then just excite the L plus 1 mode, you start to get this logarithm. So we'll see exactly how it's done. But basically, this is the reason why these log numbers, static log numbers in 5 dimensions, they are not 0, also because they run. Maybe you could say, I can find a scale in which I can set them to 0, but this will become non-zero for other scales. So, what can I do with this effective theory? So I want an effective action. In particular, I can compute observable, like a differential cross-section of the scattering these waves of this group. Okay? Or, scattering matrix. You can use this exponential representation of the scattering matrix and compute this scattering phase in the effective field theory. So that's something that you can do order by order in the frequency expansion. Gm omega, for instance, in 4 dimensions, you have like a solid line with black lines like the word line, and then the dotted lines like gravitational chain between the word line and the blue line, which are like wave, scalar wave. Gravitational chain to gravitational chain, the gravitational chain. So 3 loops, we start to have the contribution from our contact operators in our action. And those contact operators are very important because this triangle diagram that having there has a UV divergence. It means that you do this Feynman integral, you have a divergence. That's why you have, if you do this in dimensional regularization, you have this 1 over epsilon for D. And you need to regularize that divergence, right? That's why this divergence. So something that's been explored by other people, the Martin collaborators, and it's been extended by other groups like Simon Cowell, using, instead of solving for the scattering amplitude using Feynman diagrams, they use the old way of solving observable, which instead solving a wave equation, effective wave equation. So before we knew quantum field theory, we compute observable over solving wave equations. So they use that trick to go very high up. So anyway, with Christopher and collaborator, we wanted to use the same trick that the same machinery that the Fabian collaborator used. We try to understand a little bit the response of these scalar black holes to scalar perturbation. So, in 5 dimensions, you have again one gravitational exchange, 2 gravitational exchange, the contribution from the contact term in the effective theory. And again, like in the 4 dimension, now in the 5 dimension, you have a UV divergence from this time. So this UV divergence shows up actually earlier in the small frequency expansion. And you have to regularize these numbers that you introduced there. Now they're going to be depending on this regularization scheme that you use to regularize that divergence. So let me stop there for the effective field theory. Let's say I wrote an effective theory on how this object reacts to external perturbation. I have a prediction for an observable. It's going to be depending on these effective log numbers. And now I'm going to concentrate in the UV theory. So it's something that many of you have. So this is black hole perturbation theory, right? And there are talks that we're going to talk about something related. There are many posters about the computations in black hole perturbation theory, flat space, flat black holes, but everything is the same. So you want to know the details of how this computation goes, you go and read the poster. So again, I'm concentrating the simplest kind of perturbation, scalar perturbation in this Schwarzschild black hole in generic spacetime. So perturbation just comes to solve the wave equation for this scalar field in this background. It's a differential equation that looks at Schrödinger type of differential equation. You have a potential similarities. Particularly in the next dimension, you have 3 similarities to this differential. You also have taken advantage of the spherical symmetry to separate the differential equation. Spherical harmonics and then the radial equation has the information about the dynamics. So 3 singularities, 2 regular, 1 irregular, 2 higher dimension 3. And in 4 and 5 dimensions, you know what they are. Right? So 4 dimensions, the differential equation is a confluent point differential equation. And in 5 dimensions is the reduced confluent point differential equation. So it's a little bit simpler in 5 dimensions. The only thing that you need to do is to find what is the dictionary that maps the parameters in this representation of the confluent point or reduced confluent point to the black hole parameters. In particular, 4 dimensions you have these 5 parameters, 5 dimensions you have these 4 parameters. L here is the angular momentum contributions. But now this differential equation that you're writing is keeping omega generic. It's not setting omega to 0, for instance. I'm studying only static perturbations. I'm interested in studying more generic time dependent perturbations, so we're trying to keep. The way we're going to solve it is by doing an expansion in So, of course, I'm sure that if you do other spin waves, the differential equation is exactly the same. The dictionary is the only thing that changes a bit, but the other things is exactly the same.
This H, this 1 over d minus 3, is true also for IRB, like
Yeah.
for the equal
Really,
get 1/4.
yeah, you start to get like a fraction runs. That's very good. Okay, so you want to solve this differential equation? Before the back in the 90s, people doing general relativity computation figure a way of solving this differential equation. So it's the method of Manu, Suzuki, and Takasugi. So what they did is expand the solutions around the singular points. So the singular point at the horizon and the singular point at infinity. Right, the combination of Coulomb or hypergeometric functions, and then you have this infinite series. So by matching this series in some intermediate region, then you find a three-term recursion relation for these coefficients, and then you can find an algorithm to solve these three-term recursion relations. So for instance, the way they did it in the original paper is expanding them to powers of g and omega, which is very similar to the post-Minkowski expansion we do in the binary graph approach. So the lines really nice. So, of course, as many of you know, we now have different way of solving this differential equation, either using a gauge theory language, cycle Witten course in many pastoral symmetric gauge theories, or two-dimensional conformal field theories, in the unit in which you have an infinite central charge. You can find the same type of differential equation in this other scenario. So basically, you can map the general relativity computation to gauge theory or CFT kind of computation. So the nice thing about this is that it gives you a different way of interpreting the solutions, and also gives a different way of doing kind of resumations. In the end of the day, what we're going to see is basically that this new type of function that solve this point differential equations or constant point is related to this method. So depending where you are in 4 or 5 dimensions, you have more or less masses and multiplets. The renormalized mu, which was the renormalized angular momentum in general relativity, as an analog with this theory is the quantum cycle, quantum period. So, so in this paper with the our paper with the Christopher and the others, we found the formula for what the scattering amplitude for this scattering of waves of black hole will look like. So, but this is the UV solution now. So before I was discussing how an observer at infinity will look this scattering process. Now this is how the full UV solution, where you know everything about the source in terms of this black hole. And then the formula is, it looks much nicer than the MST formula, but it still looks difficult, right? So first of all, you have like something that we call the near and fast sum factorization. You have like a red sum contribution and a blue contribution. So the red sum basically sees the black hole as if it was a point particle. And the near sum is a function of this tidal response of the black hole, this kappa 4. It has information about how these many degrees of freedom are being excited near the horizon.
Excuse me, this K4 in gauge theory, what is it?
So
I missed it somehow.
I realized that actually I didn't put the explicit form of K4, but this is just a combination of gamma functions and this, with the different mass insertions.
It's not with the PP.
So it's a little bit messy because these are 4-dimensional perturbations, meaning that you have things like the Newton phase in there. It's like an exponentiation of the area of the vertices in the theory, and this F is what we call the Nicholson function M and N, which parameters that are related to the black hole parameter. So that's the 4-dimension. And then if you look at the 5-dimensional formula, it's way simpler, right? The far zone is just a function of the renormalized angular momentum. There is no IR divergences, there is no Newtonian phase in the far zone, everything is machinized. There's still some near zone contributions, some finite size, the formation of the black hole in 5 dimensions. So the physics is more or less the same. So, what is exactly that I'm computing here? Actually, I realized I didn't write it. So before I wrote I was computing the effective field theory. And I was computing this n order by order in the wave expansion. That was my EFT prediction. And now in the UV, what I'm computing is the same scattering amplitude, but in partial waves. And I'm writing as some absorption parameter times into the delta and some phase shift. So the phase shift is just the argument of that formula, the phase shift is just not of that formula. But this is something that you can extract order by order again in the low frequency expansion. And then, for instance, you can start matching this guy, and absorption will come from the absorptive operators in the effective Lagrangian. They will be matched with this part of the UV computation. Once you match the two, then you can extract this log number. So, something very important about this formula is that this is a Gaussian-dependent, Gaussian-variant formula. So it just basically the connection of the singularity at the horizon and the singularity at infinity. So it is the same formula regardless what is the type of coordinate you use to write the differential equation. So it's really like a Gaussian variant formula. So any matching in your effective field theory to this formula will remain the same in any type of coordinate system that you use. So the numbers that you extract from this matching are Gaussian variant numbers.
Why that absorptive part coming also from the far zone?
No, actually, we will know. If you compute the mode of this part, you're going to see that's why. So the absorption really comes from this.
And the frequency dependence is just this factor?
The frequency dependence, it comes in every single parameter of the differential equations. What you have to do is solve this. I don't think if I put the frequency shows almost in every parameter of the differential equation. So you take this big formula and start expanding it around here. Very soon. Or the Bayerian G omega, and then you match the effective field theory computation of the Bayerian G. So you may ask, if you have this contact operator in your EFT, maybe you could just match them to the near zone contribution. And that's what people used to do back in the day. Maybe you don't have to care about far zone loop diagrams. You can just fix this number by matching the near zone. But this is always true only when this separation of the near zone and far zone is true. And this is only true for the 4 dimensions. It's only true for the static log numbers. So actually, the static log numbers that people used to compute in general relativity in this way, they were correct. But when you have dynamical log number, this near zone far zone separation mixes together. So you start to see that if you evaluate the near zone contribution in some harmonic, let's say n equals 2, n equals 3, then you start getting divergences when L is an integer. So those divergences will cancel once you add the far zone contribution. So that's basically telling you that if you want to extract finite number out of this solution, you have to consider everything together. You cannot only match near zone to extract this number of numbers when the contribution mixed together. And that's exactly like this mixing is equal to the renormalization group freedom that you have in these coefficients, in these effective coefficients.
A question. So I understand that the full result is gauge invariant.
Yeah, the EFT is also gauge invariant.
But is the tidal response function defined this way gauge invariant as well?
This K4, I'm not really sure because this K4, what we are doing here is kind of cutting the space-time somewhere and say, okay, this is the contribution near the black hole. But as I'm telling you, if you cut, maybe, depending where you cut, you will start inducing divergences. So I'm not really sure that defining a Taylor response function is something well done. Unless you make sure that there is no mixing, right? So you code exactly where the true separation happens. But when there is running of these numbers, it's something that I see is very difficult. Okay, so before I do the matching, let me actually go to the Taylor response and study this a little bit. So for black holes in 4 dimensions, the leading corrections in the GM omega expansion, they look like this. Actually, is GM omega to the 2L plus 1, which is very similar to what the form of these effective coefficients in the effective field theory will look like. And then this combination of gamma functions. So if you evaluate integer L, you realize that the expansion gets pushed one higher order in the PM. So if you wanted to fix something in 4 dimensions, which is the static contribution something like R to the 2L plus 1, to the R to the 2L plus 1 contribution in the Nielsen Taylor response function, you'll realize that you're matching to a 0. So that's the 0 that is responsible for setting to 0 the static log numbers of trashy black holes. But that's something that happens only because at this order in the PM expansion, you're not inducing any divergences in the cutting of the Nielsen and Farsa. So instead, if you do this in 5 dimensions, the contribution to the Taylor response function again is g omega to the 2L plus 2 now in 5 dimensions. Then combination of gamma function, you evaluate for even L, you get number, for odd L, you start getting these poles, 1 over L minus n poles. So really telling that this tidal response function in 5 dimensions is not, if you call it just like that, it's not well defined. But if you, of course, this pole will cancel once you add the Fabian contribution. Nevertheless, if you put this extra factor, 1 plus these phases in the K5, you get the sine of pi L. This sine of pi L will be 0 for integer L. So in particular for even L, you will get a 0. So the series will get pushed one higher order. For odd L, well, you get a 0, but then you get a pole, so you have to do the computation together with the Fabian contribution. But this analysis more or less tells you that you should expect that log numbers in 5 dimensions for even L, the formation they are going to be also 0. Because they are pushing, the series being pushed one higher than the PM expansion. Whereas the ones that have odd L, they will present some kind of renormalization group running, because you are having this pulse in the Taylor response. But of course, the analysis has to be done by considering the full matching of the solution, right? So I have an effective field theory computation. This is just a triangle diagram. You have to put all of the others together, the contact terms. Then you need to match with the solutions of the black hole perturbation theory. So in particular, I'm showing the results for log numbers in 5 dimensions, and I'm putting some generic boundary conditions at the horizon when I'm solving this differential. Maybe there is a bit that is incoming in the horizon, maybe there's another bit that is outgoing in the horizon. Last thing about the log numbers, the elastic part of the log numbers is that they are independent of these boundary conditions we reach the horizon. In particular, at this order, I have 3 log numbers. So the L equals 0 omega 0 number, which is 0. It's 0 also because of the shift symmetry of the effective action that I'm writing. But then the L equals 1 omega 0, which is like L equals 1 static log number, is not 0. So when I match to black hole perturbation theory, I get this number. This number is now a function of the normalization.
Is this consistent with all the not here, all the...
This is consistent. the previous computation that people have done for this rounding of this log number has been the beta function, for instance. So you take the derivative with the log mean, and you get the same result. Now, but the matching to the full computation, which allowing you to do, is to fix also the constant contributions. So again, these constant contributions, they depend on the renormalization of the regularization scheme that you are using to do this Feynman integral. So in particular, we did this Feynman integral in dimensional regularization, and then we store this 1 over epsilon in the MS bar scheme. Just you know, the regularization scheme which just work. People can do it in other schemes, but something we are having in mind to reuse this to do binary black hole computations. So people in binary black hole computation, they use dimensional regularization. So then you also have some absorptive numbers. So for instance, you see C omega. It does depend on the type of boundary conditions of the horizon, purely ingoing, purely outgoing. If it is some kind of reflective boundary condition, just get zero absorption. So, but this is what really mean when we said, you know, log numbers of black holes in 5 dimensions, they are not zero. But I mean, you know, there is a number which also runs. Right? So, in 4 dimensions, there is other computation that people have done, they have done exactly the same thing, and found zero log numbers for 4 dimensions static, and then zero log number. Oh, yeah. It's almost time. So, but you know, maybe in the next 5 minutes or so, if there is 5 minutes. Because I've been telling you basically about you know, scalar perturbations of black holes, and I started the talk saying, you know, we're going to do gravity. Well, I should tell something about gravity. Right? So, particular, again, we want to prove finite size effects at order G5, which is in the case of gravitational wave scattering of black holes, is a 5-loop computation. It's a very difficult computation, and we are not there yet. But we have started this program, and we are slowly getting there. So what is it that we are doing in gravitational wave scattering? So we have a black hole, which we model as a point massive word line. And then we couple that word line to gravity. In particular, we send gravitational waves scattering of this point particle. And then we compute, you know, the scattering phase order by order in the GM omega expansion. So 3 level, something very easy to do. 1 loop you have 3 integrals that you have to do. The 2 loops you have 6 massive integrals. You have many diagrams contributing to the scattering phase, but then you realize that not all of the integrals that you have to do there are independent. They are related to one another. So that's what people call usually in the scattering language like integration by part deduction, until you get, you know, the really linear independent integral that you have to do. They're just linear. The nice thing though is that, well, this is just a 2-loop. I told you the finite size effects will show at 4 loops. So of course you expect this to be with the Farson contribution from the UV solution, and we did check that it matches perfectly well with the Farson contributions. The set of functions that you get is only multiple polylogarithms as theory. But as I'm telling you, you know, if you want to prove this CE coefficients, for instance, you have to do a 4-loop computation. The CE first one, well, you kind of know that it has to be 0 because there is no near some Farson mixing of the UV solution. Nevertheless, it's fine to try to do it, right? There's a nice paper by Alessandro and Julio who approached this problem how to fix these numbers from looking for symmetries of the effective action. It's a very nice discussion about the asymmetry, spurion symmetry that is protecting these numbers. We also want to explore those by doing the full matching and trying to understand maybe how the symmetry may arise in this big formula from the MST solution eventually. So we are not there at 5 loops yet, but we are on the way. So maybe I'll stop here because want to say something about spin, but it's already too well.
Thanks for the talk. Questions or comments?
So I had a question. At some point you mentioned that you could match the small, let's say, GM omega expansion from the EFT with the one from the instanton expansion. Do I understood correctly? Like you can do order by order in GM omega,
Yeah.
precisely the match?
Actually, the instanton expansion is equivalent to the GM omega expansion. This is right. So the instanton expansion is a frequency expansion. GM omega.
Well, but you have like A.
So yeah, so what you do, but in practice, what you do is first you solve the differential equation order by order in lambda, or else and you call it, and then on top of that you do then an expansion in omega, because also you have
Yeah, what I was thinking was that in the instanton expansion of A, once you add instantons, you are recorrecting each order in
you
the
make
small
sure that
omega.
you make sure that you introduce the corrections of M.
But so you can avoid resumming instantons, basically?
Where is something?
I mean, in the A expansion, you have also some coefficients in front of lambda. And if you take the small omega expansion by considering also those
You
coefficients,
mean the portion on over L? Or?
no, just
No,
the small omega
this is
expansion.
the A cycle.
Yeah, or also F if you want, but apart from lambda, you have some other coefficients, and if you just take the small omega expansion, if I'm not wrong, each instanton that you add will correct also the smaller omega
Yes,
terms.
yes.
So I was just wondering how you could really match the small GM omega expansion from instantons with the EFT, which doesn't care about corrections, I guess. I don't know.
Again, what we do is we basically we write the solution order by order in lambda. We should show the formula exactly what we're doing. So in this formula, you know that this A, as you were saying, of the F, it gets a correction with GM omega, right? In particular, this A is probably something like 1/2 or 1/4 something like that, I don't remember. But the other class corrections for their GM omega. Or you could say corrections in lambda. So first of all, what we do is we write the corrections to A to a given order in lambda, the same the corrections to F to a given order in lambda, we plug them in the equation and then we span in GM omega. That's what the dictionary.
Yeah, my question is if then you add one more instanton, I think you are changing also the previous orders that you already computed in the GM omega expansion, not in the lambda. I mean in the GM omega. That was
No,
Yeah,
no,
I mean-
that's not the one.
Are you sure?
Yes. Because you always have an higher power of lambda, and you only get actual.
I think so.
This will define it.
I'm not fully sure, but okay, we can discuss maybe. So, thanks.
I have another question. So this is a very compact formula, but how much you can make it explicit? Do you need to rely always on expansion, or can you put in a computer and evaluate for example?
Wow, I would love to. So far, the way we know how to use this formula is basically writing the instanton expansion of F from A, and then truncate it at some order, and then use expansion. It would be amazing if we could write this formula, maybe a numeric solution to this formula.
Is it feasible, or you think it's too much?
Is it feasible?
I'm not sure, maybe.
Maybe. Okay.
Yeah, that would be very nice, because then they'll give you some kind of analytic understanding of the analytic properties of this app.
Is it possible? I mean, these F, for example, can also be computed from some TBA. Right? And is it possible that at least numerically one can write this by solving some TBA equation?
What's the
Thermodynamic data, like some some nonlinear integral equation whose solutions can then be integrated to give that. And this is like in the original paper from Castlefin, which is really, but I don't know to what extent it's been used in this context.
I'm not very familiar, but if you think that this is possible, that would be amazing. I mean, it would be very interesting if there is like some kind of numerical integration of this solution.
I'm not sure how applicable it is. I know in principle that in gauge theory context these things are available. I don't know how useful they are here.
If there are no more questions, we can thank the speaker again.